I'd like to explain a little bit about what's going on under the hood with our implementation of vector search and how you can use that information to make better decisions as you build applications on top of it. The first thing to understand is that vector search is built on top of SAI, or rather it's built as a part of SAI. SAI stands for Storage Attached Indexes, and it's a next generation Cassandra index coming in Cassandra 5.0, and it's available now in DataStax Astra. SAI gives you a couple things. In this graph, we're showing the effects of indexing a billion rows with 10 indexes defined across the rows in that table. On the left is the space used by the raw row data itself. So that's about 160 gigabytes of data. And then we have in red an experimental kind of index called SASE. In the green, we have traditional Cassandra secondary indexes. So that's what you get if you download Cassandra 4.0 and you say create index, whatever, the green bar is what you get. And then the blue is the SAI index. So you can see that SAI is more efficient by a factor of about 5 compared to the next closest index implementation. The other thing, maybe even more important, is that with SAI, you get much more powerful queries. The traditional indexes, the green ones in the last graph, could only index exact match queries, and they can only combine predicates using AND. So you could select column 1 equals X and column 2 equals Y, but you cannot select column 1 equals X or column 2 equals Y. You couldn't do that before. You can do that now with SAI. And you can also do inequalities with SAI, and you can also do nested predicates with SAI. So here's an example of doing nested predicates with an OR using SAI. That's completely legal. You can do that today, again, in Astra. So we're going to apply this to indexing vectors. And to do that, I'm going to back up just a little bit and talk about what we mean when we're comparing vectors in the first place. So our goal is to, given a bunch of vectors that we've inserted in the database, find the closest match to a given query. And you'll see discussed a couple different abbreviations. One of them is KNN. KNN stands for the K nearest neighbors. Usually when people are talking about this, they're talking about the exact nearest neighbors. So if I've got 10 million vectors, I'm going to find the 10 out of those 10 million that are closest to the query. The thing is that to do this, you have to compare the query with each vector in the source. There's some clever tricks we can play if we only have a vector of dimension 2 or 3 or 10. However, those algorithms don't work when you start to get to vectors of dimensionality 300, 700, 1,000. And when you're dealing with machine learning vectors, which is kind of the most interesting vector to index right now, you start at several hundred. And so when you're doing vectors of several hundred dimensions, brute force is the best we've been able to come up with to get exact matches. And so naturally, when you start to get 10 million, 100 million, a billion vectors inserted, doing that brute force gets less and less attractive. And you can actually get down to logarithmic queries if you are willing to say, I can live with approximate results instead of exact results. So this is usually abbreviated ANN, approximate nearest neighbors, and we can do logarithmic query time with that. So when we're there's a bunch of different implementation options for getting logarithmic query results. But when we're applying this to Cassandra, we've got some specific requirements that we need to meet that narrows down our options. The first is that we need to have reasonable performance from disk. If the index only really works when it's 100% in memory, then it's not a great fit, because in Cassandra, we're typically dealing with billions of rows. And so we don't want to have to spend enough money to fit all of that in memory. The second requirement is that the index needs to be incrementally buildable and immediately queryable. What I mean by that is, as I insert rows into my table, I should be able to do that one row at a time. And as soon as I've inserted that one row, I should be able to use it in a query. I shouldn't have to do batch inserts of thousands of rows. I shouldn't have to wait for some kind of indexing process to happen in the background. I want it to be available as soon as I've inserted it. And then finally, we don't know the data set in advance, and some of these index implementations for vectors, they only work if you do know that in advance. And so those get ruled out as well. So this is a graph of some of the index implementations in Facebook AI's approximate similarity search library. There's literally dozens of combinations you can put together here to test. And what you're seeing on the axes, by the way, is the x-axis is recall. That's how accurate are my results. And that's measured as a percentage or a fraction from 0 to 1, where 1 is I got 100% perfect results. And then the y-axis here is how many queries per second I can do. And the y-axis is logarithmic. I'll point that out as well. And so all of these index types, you can trade off between how accurate do I need my results to be and how fast do I want it to be. But there's clearly some algorithms are better than others, even given the fact that we can make different trade-offs. And so applying the criteria that Cassandra has, we end up with basically one appropriate candidate for building the indexes. And that's called Hnsw, which stands for Hierarchical Navigable Small World. And the idea here is similar to a classic skip list, where I'm going to create multiple levels in my index. And at level 0, the bottom, all of my vectors live in level 0. But every level I go up from there, I only promote 10% of the vectors to that next level. So I've got 100% of my vectors in level 0. I've got 10% in level 1. I've got 1% in level 2, 0.1% in level 3, and so forth. And what we do is when we search for a query vector, and the page here is giving an example of a query vector in red, what we do is we go to the top level in our index and we compare it to the nodes, the vectors in that top level. And then the one that it's closest to, we look for the neighbors of that node in the next level down. And then we take the one that it's closest to in that level, go the next level down, and so forth, until we get down to the bottom level where all of our vectors live. And we've narrowed down the vicinity of where we're going to look by following that chain down from the top. And so it's not an exact search again, because we're only remembering a small fraction of the potential neighbors for each vector, first of all. And then second of all, we're bounding how far we search on each level. But you can see how we get the logarithmic behavior from the graph construction of 1/10 of the nodes on each level. The details of how we build that, if you're interested, I definitely encourage you to read the paper that this comes from. It's super readable. The core of the algorithm is just about 1 page. So at its core, it's very concise and simple and elegant. I won't go into it in more detail here, except to say that this is something that we can do concurrently and give you those logarithmic query results. So some more details of our implementation is that this is actually based on a Hnsw index from Lucene, but we've made a few changes because Lucene does not qualify for one of those requirements that I gave of when I add a value to the index, it needs to be immediately queryable. Lucene is built around more of a bulk ingest kind of design, and it has what's called a commit interval. And that says we're going to go through and serialize all of the data that we've had in the last interval and make that available for queries. But until we do that commit, it is not available for queries. So there's a time window where I've inserted my new record, but I can't see it yet. So that's not a good fit for Cassandra. And so what we did is we modified the Lucene index structure to be able to index that and query that without having a commit delay. And as part of that, we were able to handle not just doing reads instantly, but doing reads while writes are happening at the same time, and even multiple writes happening at the same time. The last thing is that I mentioned that disk, serving this index from disk is also very important to Cassandra. And so we took a look at how we cache parts of the index in memory, and we adjusted that as well. And so what our strategy is that since the top levels of the Hnsw index are accessed more frequently, we're going to preferentially store those levels in cache so that we're not having to read from disk as often. So putting those together, we have a vector index that's part of our SAI implementation. And so you can do a simple give me the closest vectors anywhere in the table. That's this first code fragment here, where I'm just going to say, I'm not specifying any other predicates. I'm just saying, give me the closest vectors. So here's the syntax for that. I just say order by my vector column name. The column name here is embedding, and then ANN of my query vector. So the question mark would be the bind variable that my query vector gets attached to. And then I can say, how many results do I want? That's the limit 10. So that's the simplest version. The next one is that maybe the most common kind of predicate in Cassandra is I want to limit this to a single partition of data. So here I've added where partition ID equals some other bind variable. And so that, that composes with the vector ordering that we get from our index. And then we can also include other index predicates with or without a partition ID. And that's what this third example shows is, I've got that nested Boolean query, and then I'm saying I want to order that by vector similarity. So we can do any of these, all of these, and it just works. So our philosophy is that vector search is a feature. It's an important feature, but it's not the only feature. You want vector search to play nice and be part of the rest of your database and compose with what the rest of your database does. Your app needs to do normal CRUD operations, create, retrieve, update, delete, and also vector search. Typically, vector embeddings are derived from the rest of your app data. So the most straightforward way to deal with that is to add a vector column to your existing table and then put the embedding into that column instead of doing it in a separate system. If you do it in a separate system, now you have to deal with all the pain of keeping those in sync, two different systems to administer. It's just this is why the history of databases has been, I want to use the smallest number of systems as possible that let me accomplish my goal. And then it helps that the ordering by vector similarity is a natural extension of CQL, the Cassandra query language. And then, as part of our implementation, we designed it that such that it's not going to surprise you. Reads and writes can happen concurrently. Data is immediately queryable on insert. It composes the way you'd expect with other predicates. We want this to just work as much as possible. So a few implications for building your application. So the first is that as far as performance is concerned, the most important variable is how large your vectors are. So I put 3 examples on this page. Probably the most well-known at this point, I guess it's kind of the default for a lot of people now, is OpenAI's Ada embeddings model. And that's going to give you vectors of 1576 dimensionality. Google's Gecko embeddings, which are based on their Palm architecture, are going to give you half that size, 768. And these are competitive in terms of precision, like in terms of distinguishing actually similar pieces of text. Gecko is competitive with Ada. And so other things being equal, I would prefer to use the Gecko embeddings, because every time that I'm doing a comparison as I'm navigating down that search index, I'm computing a cosine or a dot product of my query vector with the vector in the index. And so it's literally twice as slow to do that with 1576 dimensions as it is with 768. I've got one more model on this page, and that's the Mini LM L6 model from Hugging Face, and that's half the size yet smaller of the Gecko model. Here is where we do start to see worse performance on the dimension of how good is it at distinguishing these pieces of text. In my opinion, you should use a model like Mini LM L6 carefully, because if it does give you enough distinguishability across the vectors, then great. Like you're faster and you're less expensive. So if it solves your problem, definitely use it. However, I would not put it in the same category of you can probably just use it and have it just work like the other 2 larger models. The next thing is that you should use normalized vectors and dot products instead of unnormalized vectors and cosines. And all that means is that if your embedding vectors have been normalized to length 1, then we can compute the similarity as a simple dot product between the components of those vectors, which is mathematically more efficient than computing the cosine between 2 large vectors. All of the models on the previous page, they give you normalized vectors. So you should use dot product. And here's the syntax that you use to tell Astra that you want to create an index that uses dot product. So that will give you a performance difference about 40%. It's about 40% faster if you use dot product than cosine. So that's material. The reason that we don't make that the default is that if your vectors aren't normalized, and we have no way of knowing ahead of time whether they are unless you tell us by using this syntax, if your vectors aren't normalized, then dot product will give you effectively nonsense. And so that's why we default to cosine. But in general, check to make sure that your model is giving you normalized vectors, and then opt into the dot product. Another thing is that you should avoid deletes if possible. So if it's not possible, then it's not, and Cassandra will handle it just fine. However, it does become less efficient, and that's because of how the index works. Remember that the index is basically a graph of nodes representing each vector and the neighbors of that node. And so if I delete a vector, there's no way to pull that out of the graph without causing collateral damage. And so what we do is we leave the vector in the graph, but we mark it as, hey, this has been deleted, it's not used anymore. So deletes work, but it does make things slow down because now I have to go and check and say, hey, is this vector actually still valid? But if you don't do deletes, then we don't need to do that check and it's faster. Another piece of advice is, this applies to all of Cassandra, not just vectors, is that Cassandra is designed for concurrency. And especially when you're adding data to the system, I'd say 90% of the time, our inclination as programmers is to write code that looks like this, where I'll prepare my statement because I know that that's more efficient than making Cassandra parse it fresh every time. But then I'll go through every item in my collection and execute that prepared insert with that item. That will work, but what that means is that I'm sending a request to Cassandra, I'm waiting for it to get back, and then I'm sending another request, waiting for it to get back. And so, I've got, this server of, dozens of cores on the other side of that request, and I'm just doing one at a time with all the latency of the network in the way of doing that. So it's much faster if I just do those inserts concurrently. And the Cassandra drivers provide this functionality out of the box. So this is an example with the Python driver. So I'm importing at the top, I'm importing execute concurrent with args. And what that means is I want to execute a single statement against all the arguments that I give it in that function call. So I'm calling that with my session object, with my prepared request, and then I just give it my collection of tuples of data to apply to the bind variables in my statement. And now the driver can go and do that. It will parallelize that and issue multiple requests concurrently. So this is kind of the tutorial version of this code. In the next slide, I'm going to show you a more realistic version, because in the real world, sometimes requests fail because the server was overloaded or because there was a network hiccup. And so we want to be able to deal with that without starting over. And so this is actually from some code I wrote over the weekend, just playing around. And you can see a couple differences from kind of the tutorial version here. And I've bolded a couple of those. So the first is that when we're running that function, execute concurrent with args, I want to specify how many requests in parallel do you want to make. That's the concurrency argument. And then the second one says, don't just give up if you get an error. So the default is, as soon as I get an error, I'm going to throw an exception back to you. But that's not what we want. We want you to keep going. And then when you're done, give me for each request, did it succeed or fail? So then that next line there, where I've got the list comprehension, I'm saying, go through all of those items that I sent the database, the chunks that I sent the database, and then associate it with its success or failure result, and then pull out the ones that failed into a new list. And then we'll loop again with only the failed ones, we'll retry those. That's what's going on there. Oh, another easy way to improve your performance is to do your reads at consistency level of local 1. So the default consistency level is quorum, which means we're going to compare results from 2 out of 3 replicas. But this is not the best thing to do in the case of vector data, where we usually, depends on your application, but almost always in the case of vector data, it's not something that you change frequently. Typically, your vector embedding is computed based on the data in your row once, and that tends to live a long time. And so, rather than wasting time checking 2 replicas that are pretty much guaranteed to have the same data on them, we'll just request that Cassandra check a single replica. So that's half the work. It's twice as fast. It's just a good idea. The last tip I'm going to leave you with also depends on a little bit of understanding of how Cassandra works. And I referred to this earlier when I talked about how often when we're querying indexes, we'll want to narrow down what the index has to search by giving it a partition ID. Now in Cassandra, you can partition by user, you can partition by time, you can partition by lots of different strategies, but the bottom line is by specifying that partition, the index doesn't have to do an exhaustive search. It can limit its search to that one partition. And so not only does that matter on an individual replica, but it also means that Cassandra has to check fewer nodes in the Cassandra cluster because each partition is uniquely assigned to a triple of replicas. And we know that we only need to touch those specific replicas. So if your data model is appropriate, then giving this hint to the query is going to make your workloads more scalable, as well as giving you lower latency for each of those queries. And so with that, thank you, and I'll turn it back over to the team.